All right, so we've dealt a lot with inelastic collisions where things stick together, but we haven't dealt so much with elastic collisions, specifically where things bounce off of each other. What's special about elastic collisions is that both the kinetic energy, so not just Ke plus Pe, but the kinetic energy and the momentum are conserved. So if you find the total kinetic energy at the beginning of a situation, it is the same as the total kinetic energy at the end. Now that's only for elastic collisions where things bounce off each other. Okay. Now what can sometimes be confusing is there are situations where the momentum equation is not enough. You'll find that you have more than one variable you're missing. And if it's an elastic collision, you can go back to kinetic energy and try to see if kinetic energy can help you find what you're missing. So first, a really simple example I'm just going to talk through, not do the math. Let's say we have this cart that smacks this other cart that's not moving, so this one is at rest. And then once they hit, they both move off in the same direction. So they did bounce off each other. This one bounced that way. This one kept going this way. So they did bounce because one moved off to the right. Bouncing off each other doesn't mean they have to move off in opposite directions. And if you were given this problem, you could definitely use momentum conservation to solve this. M1v1i plus M2v2i equals M1v1f plus M2v2f. So if I told you the initial velocity of the mass, this one's at rest, and then I gave you the velocity of either of these, you could then find the missing velocity. But it may not always be that simple. Let's complicate things a bit. The problem with two-dimensional collisions is they're going to be really hard because you have a lot of things that you might not know. So if you're trying to find velocity in x and in y, and let's say this picture right here is a two-dimensional collision. You've got this one object here that hits this other object, and then they both move off at some angle. When that happens, if we don't know the final velocity of this object, that actually means there's two things we don't know. We don't know v2f x, and we don't know v2f y. So we might have a lot of things we don't know instead of just one, meaning that we might have to find out some information before we can use momentum conservation. And for that, we'll have to go back to kinetic energy. So I'm just going to do this example, and hopefully you'll see what I mean by we might have to find out some information and go back to kinetic energy. Here we go. Let's say we want to find the velocity of object 2 at the end of this problem. Well, the problem tells me that the velocity of object 1 is 1.5 meters per second. And let's go ahead and assume we know the mass of these objects. Let's say that the mass of both objects is 7 kilograms. So mass is 7 kilograms. Okay, so now I've got the velocity of the first object and its mass. So if I wanted to, I could find its initial momentum, I could find its initial kinetic energy. Notice that this velocity is pretty clearly in x, and let's go ahead and declare a coordinate system, y and x. The easiest thing to do now would be to find the velocity of object 2 not split into x and y using energy conservation. Because, as I told you, since these two objects bounce off each other, kinetic energy must be conserved. So let's try that. So I know that kinetic energy at the beginning of this problem is going to equal kinetic energy at the end. The only thing that has kinetic energy at the beginning of this problem is that first stone. So Ke I equals 1/2 7 kilograms times 1.5 meters per second squared. So the initial kinetic energy is 7.88 joules, if you multiply that all out. Now that has to be equal to our final kinetic energy. So at the end of this problem, I see that stone 1 has a velocity of 0.61 meters per second. Let's see if we can use that to find the final velocity of stone 2. So KE final at the end is 1/2 the first stone times its final velocity squared plus 1/2 the second stone its final velocity squared. We're not worried about splitting into directions just yet. Okay? So my final kinetic energy, I already know, is 7.88 joules. That's equal to 1/2 7 kilograms times 0.610 meters per second squared plus 1/2 second stone 7 kilograms V2 F squared. And now I find out that, let's kind of move this over here so we can have a little more space. 7.88 joules equals 1.30 joules if I multiply that all out, plus 1/2 7 kilograms V2F squared. If I subtract the 1.3, multiply by 2, divide by 7, take the square root, so if I just solve that out, I get V2F equals 1.37 meters per second. Okay? So I've found its final velocity, not split into x and y, using energy conservation. But now, if I'm truly going to find this object's velocity, I not only have to know its speed, I also have to know the direction it went, so I need to know its angle, which means I'm going to have to find both components, x and y, and then use tangent to find the angle between them, or some other trig function. Let's see how it works out. Now that we know the velocity, let's continue the problem. We can solve momentum problems in 2 dimensions. And what we're going to talk about tonight is that momentum is conserved separately in x and in y. Let me minimize this picture and type out that note real fast. Okay, so momentum is conserved separately in x and in y. This right here is the biggest takeaway tonight. So whenever you have an object that moves in one direction, hits something, and then they both move off in x and in y, you'll have to write multiple momentum conservation equations, one for x and one for y. And so you would go m1 v1 I x plus m2 v2 I x equals m1 v1 I x vf x plus m2 v2 f x. So you'd have to separate the momentum, you'd have to separate the velocities into x and y for each object involved. Now before we go any further, I've looked through a bunch of AP material to make sure this is true before I say it. But as far as I can tell, the type of problem I'm going to solve for you tonight, just to show you how this would work, because it is a nice wrap-up and it kind of shows you how momentum and kinetic energy are connected. As far as I can tell, there's not a possibility you'll be asked to do a question this hard on the AP exam. You'll be asked to do a slightly easier version that we'll actually do in class tomorrow. But the question I'm about to do for you is harder than one you will find on the AP exam. So now let's try to figure out the direction of that stone. Something that I notice is that at the beginning of this problem, there was only motion in x. So there was clearly momentum in x. But neither of the stones were moving down or up, so there was no y momentum. So I know that the y momentum at the beginning of this problem was 0. Therefore, by conservation of momentum and the fact that x and y are conserved separately, big takeaway from this video, you got to know that. I know that the final y momentum is also 0 because x and y are conserved separately. So let's see if we could figure out maybe the angle from that. What if I say that the final momentum of the first object in y plus the final momentum of the second object in y must equal 0. That would mean that m1 v1f times, and we need to get the y part here, so if this is our angle, this y part is opposite that angle, so m1 v1 final times sine, and that was 66 degrees, by the way, if you look back on the diagram, 66 degrees, plus m2 v2f sine of whatever that angle is. Next, I'm going to note something else. Earlier in the problem, we called this y and this x, meaning that down would be negative y. My second object is moving down, so I'm going to go ahead and make it negative. And then all of that gives me 0. So now what I've got, if I solve all this out, I could move this term to the other side of the equation, m1 v1f sine 66 degrees equals m2 v2f sine theta. And then I can plug in everything I've got. So let's see, that was 7 kilograms times 0.610 meters per second times the sine of 66 degrees equals 7 kilograms times what we found in the last problem for V2F, 1.37 meters per second times sine of theta. And if I solve this out, I actually get to a point where I can just find sine of theta and take the inverse sine. And if you solve all this out, you get theta is 24 degrees. So now, look at this. I've actually solved out the problem. So I have the speed, I have the direction, therefore my final velocity would be V2F, velocity, we've got a direction, so it's a vector now, 1.37 meters per second at 24 degrees below the horizontal, because it goes down. So I'm letting whoever reads this know that it's below this horizontal line is where I measured that angle from. All right, and that is our answer. Now, let's go to the next screen and just do a couple key takeaways, because I imagine that was a lot to take in, and like I said, it's harder than what you'll be expected to do. All right, here are the key ideas. Momentum is conserved separately for x and for y. So anytime you have objects that end up going off in both up and down directions, you've got to split both of them into their x and y components, split either their velocities or their momenta. And also, in an elastic collision, both momentum and kinetic energy, so kinetic energy at the beginning equals kinetic energy at the end, and total momentum at the beginning equals total momentum at the end. Also note, kinetic energy is not a vector, so we can add and subtract, we can add it without worrying about direction. So if we were finding kinetic energy at the beginning, we don't have to worry about, wait, does one get subtracted because it's in the opposite direction? However, momentum is a vector, so if you're adding it, you do have to pay attention to direction, because one of them might be negative with the direction. So kinetic energy will not be negative, it is not a vector. Momentum could be negative, it is a vector. And also, we would never split kinetic energy into directions because it's not a vector. You can't split it up into directions, can't do that. But momentum can be split into directions because it is a vector. All right, that was a lot, kind of a long video. These are the key takeaways. Make sure you got this. Maybe even rewind back 2 minutes and watch this slide again. And we're going to practice this tomorrow. See you then.